I just jump on to what I want to talk. So the thermal infrared instruments are designed to measure the thermal radiation from a planetary surface in the spectral region roughly between 7 to 50 micron to map the surface composition mineralogy of a planet. Most spectrometers are instruments or cameras that flown to explore different planets in the solar system, mainly focus on the 7 to 14 spectral region at either multispectral or hyperspectral mode. To name a few, we have the Mercury radiometer and thermal imaging spectrometer on Bepi Colombo will map the thermal infrared spectra of Mercury in a hyperspectral mode. And we also have Diviner of Lunar Reconnaissance Orbiter has been mapping Moon for more than a decade in the spectral range in a multispectral mode. And we also have a few spectrometers on Mars. The recent one is the Emirates infrared spectrometer on Hope mission, which is also mapping the thermal energy on Mars. How do we actually try to map the silicate mineralogy from this thermal infrared spectra? To do that, we rely on three major features. The one is the CF position. The CF position, which is the emissivity maxima in any thermal emission spectra, and this maximum occurs when the refractive index of the sample reaches the refractive index of the medium. And then we have Restsrahlen bands happens just longer to the CF band, and they actually happen to be the fundamental vibration, the stretching and the bending vibration modes of the SAO bonds. So the vibration of, the stretching vibrations happen between the 8 to 11 microns roughly, and then the bending modes happen after 16 microns roughly. And then we have a transparency feature. This is due to the volume scattering within the sample, and they're only mostly pronounced when we have samples with very fine particle grain size. However, among these three, the CF, the Christiansen feature, has been widely used to identify silicate mineralogy of a planetary surface. To say Diviner has three channels that mainly to focus this, the CF position. So if you see this plot, it's a ternary plot of just focus, ternary plot of focusing three mineral groups, the olivine, the pyroxene, and the plagioclase mineral groups. And if you try to plot the CF, just calculating the CF position from the data, roughly we say we'd be able to map the silicate mineralogy. So the data points, what we see here are the samples from Apollo missions like 11, 12, and so on. And however, if you really focus closely on these plots, with just the CF position, we can have mineralogy of a variety of combinations. So just having a CF position may not really help us to map the silicate mineralogy in an unambiguous way, or can be. So to answer that, we use two planetary emissivity chambers. The one situates at German Aerospace Center, DLR Berlin, and the other is a planetary and asteroid regolith spectroscopy environmental chamber, popularly called PARSEC, which is situated at Stony Brook. In both the emissivity chambers, we keep the sample and we heat the sample from below. And then the radiation emitted from the sample is sent to its spectrometers to measure the thermal infrared spectra. One of the major difference between these two chambers is that on PARSEC, we have a solar lamp illuminating the sample, but at DLR, we do not have that. However, we have a temperature sensor sitting on the surface of the sample so that we know what's the temperature of the sample we are looking at. And both the spectrometers have been used to measure, the planetary, at the DLR spectrometer, the chamber is used to even go up to the Mercury, Venus conditions. So what happens if we just use CF or just use RB1 to identify the spectral mineralogy, the silicate mineralogy using SiO2 weight percentage as a proxy? So what you see here is a CF versus SiO2 and RB1 versus SiO2. And in both the plots, we can see the CF and RB1 position moves shortward to this wavelength with increase in SiO2 weight percentage. And the three black boxes, what you see, or this is olivine samples, the middle one is a pyroxene samples, and then we have feldspars and the quartz. Again, if you see very closely on these boundaries, if we happen to slightly misinterpret or miscalculate the CF position, we might say an feldspathic region to be pyroxene rich region and vice versa. So, and the plots what we have is taken from very neatly, very high spectral resolution laboratory data, and then we are trying to map on a multispectral mode on a remote sensing data of a different planet. So what happens if we plot the CF and the RB1 together? So this is the new approach we are talking about. So if we plot the CF position, and if we happen to have a RB1 position and plot it against that, these data points just naturally cluster together with respect to its SiO2 weight percentages, or with respect to its mineral classes. So here we have olivines, we have pyroxenes, we have feldspars and the quartz just neatly and widely distributed, and may be helpful for us to unambiguously map the silicate mineralogy of a planet. But we need to test this plot for more parameters, right? So let's see what happens in the same plot if we have samples of varying particle size. So to do that, we took the data points from the Shirley and Bloch 2019 and try to plot on this new approach. So here we have two conditions, the one on ambient conditions and the other on similar environment. In ambient conditions, we see that with increasing particle size, only for the data points with lower SiO2 weight percentage, there's a slight shift in the CF position, but the RB1 does not really affect much. But in a simulated lunar environment, the CF has a huge shift in their position with respect to their increase in particle size. So if we do not take care of the particle size of the planetary surface or the regoliths what we are looking at, we might totally misinterpret a pyroxene of a higher particle size to a feldspathite of a lower particle size. We could really miscalculate that. And what happens, but in this plot, if you plot the CF and RB1 together, we still be able to say whether we are looking at a pyroxene or a feldspar. What happens as a function of temperature? So here, the increase in data, the increase in the size of these data points corresponds to the increase in temperature. So we have 100, 200, 300, 400, 500 degrees Celsius of the samples. So with increase in temperature, for the feldspars, we see huge shift in the RB1 position, but CF slightly, and we have both the shifts for the pyroxenes, and the olivines have some shifts in the RB1 position. But irrespective of these shifts, these minerals still sits in its own classes. So this CF versus RB1 plot will be really help us to unambiguously map whether a surface is basaltic or feldspathic or olivine rich in a more unambiguous manner. So our planned future work is to really test the robustness of this approach to see the behavior of SiO2 weight content, for example, and also the other transition metal contents, for example, moving from forstrite to firelite, or from albite anorthite series and the pyroxene series. We also want to test this plot to see how the pure minerals and the rock composition behave. To do that, we have requested Apollo lunar samples of varying bulk mineralogy content and see how that is going to sit on this plot. Can we really map the lunar mineralogy using this approach? And what happens to mineral mixtures? So can we able to say, can we really distinguish the mixtures between feldspathic and a highland or marine material, for example? And another exciting thing what we can do is that really create a CFRB FCC maps to bring out all the different mineralogies of a planetary surface of Moon, Mercury, and other things. And obviously the other thing which is very important is space weathering. What happens if we have what happens if to this plot to increase in space weathering of the samples? So we really hope this approach, and we really hope we will have spectrometers with more bands covering the CF and the RB1 spectral regions to help us map the silicate mineralogy of Moon. And we are hoping to see that in the lunar thermal mapper of Lunar Trailblazer, have 11 bands covering this region. So highly excited for that. Thank you. Questions?
Thank you very much. Thank you. Wonderful talk. We have time for a question or two. Are there any in the audience? Maybe one. Please identify yourself.
Yeah. Mike Lucas, University of Notre Dame. A very nice presentation. When you showed the ternary and then also your other CF versus RB plots, I had thought, the ability to distinguish between OPX and CPX.
Yes.
And on several year old plots, I saw that instantite and diopside plotted together, but there was other ones where the one instantite sample seemed to be an outlier. Can you comment on that?
Yes, actually, the plots what I show, it's the samples with less than 32 microns. So the RB1 position is not really pronounced for very fine particle size than the samples with the higher weight percentage. So I actually measured I measured one instantite. I took the data point from the other instantite from the Shirley and Bloch. And there are two different chambers, two spectrometers. We want to test, the plan is to have the same samples test in with the DLR system and the parsec system, which it's a two data points from different instantite, and I didn't really remeasure that. And instantite seems to be really tricky in that RB1 position for the fine particle size, but for higher particle size, we have a really nice groove that we can actually measure the RB1s. That's also on the plan.
Thank you.
Thank you.